Hi, welcome to the latest edition of Practical Pico, which is all about use cases of our latest super duper 8-channel automotive scope. I'm going to be looking at non-invasive testing on the whole immobiliser system.
And I'll be looking at 8-channel use with quad cam engine, so this is quite a common thing right now. Quad cam with direct and port injection, and we'll looking at valve timing, looking at correlation between the cam and the crank, and also the intervention of port and direct injection and where they occur in the 4-stroke cycle.
And I guess I'll be following up with the hydraulic and engine applications with 8 channels, so we can have a look at the entire system and how the two systems actually interact with each other.
Lovely. We'll be seeing you shortly.
Hello, my name's Steve Smith and I'm an automotive application specialist for Pico in the UK. Here we have the new 8-channel scope from Pico for automotive applications. It's a 4823. It's 50 volts at the front end, 20 megahertz bandwidth, memory inside there, 256 million samples. Sample rate, 4 channels is 80 million samples. All 8 channels goes to 40 million samples a second. It is 12-bit resolution, USB 3. So USB 3 of course, but USB 2 compatible. And the signal generator as well with a maximum voltage of plus or minus 2 volts. So for an automotive application, rather than now having to sacrifice channels, especially when we're looking at things like quad cam engines, multiple inputs, we can now get them all in one capture. And we've got such a capture coming up. We're looking at a quad cam engine, dynamic valve timing check. So we'll have crank on one channel, then we'll have 4 camshafts. Then we can also add things like ignition, injection, port injection, and then direct injection as well. Hopefully you'll see the true benefits of 8-channel. A typical application for the new 4823 8-channel scope from Pico, that's quad cam engine, dynamic valve timing check. There's a typical example here is 4 camshaft sensors, quad cam, crankshaft, we'll add ignition, trigger number 1. We've also got a unique arrangement with the injection. We've got 6 port injectors and 6 direct injectors as well. So there's quite a lot we can measure on this vehicle, but with 8 channels we can correlate them all together. And that's the beauty, because dynamic valve timing is pretty much the ultimate way to confirm valve timing is correct throughout the engine speed range, and also to check VVT operation as well. So a couple of things to note. It's a common ground scope, remember, so all channels are referenced to ground. So again, our test leads will allow you to stack the ground leads one on top of the other. Back pinning as well, a lot of discipline there required. You'll see in the image here that we've got a number of test leads that are all grouped together very closely, because we're probing, well, up to 8 points at the back of the ECU or wherever's convenient. Attenuation as well, we're looking at the port injectors on this, and the port injector induced voltage will spike above 100 volts, so we're going to have to use attenuation. Remember, it's 50 volts maximum input at the front end of this scope. Current clamp as well, there's no issues there with attenuation, but all the probes and all the accessories that we're used to with PicoScope will all fit on this new scope, and we can use them to correlate all the events taking place with this engine. So our setup then with PicoScope, we've got crankshaft on channel A, 4 camshafts on the next 4 channels. So that'll be bank 1 inlet exhaust, bank 2 inlet exhaust. Channel E will have ignition trigger signal. We use number 1 because number 1's great for reference. We know if we know our ignition point for cylinder 1 using the firing order, we can then map through each event during 720 degrees of crankshaft rotation. We are looking at direct injection current and port injection voltage, again for cylinder 1. So we'll have cylinder 1 pretty much locked down, but be able to look at 720 degrees of rotation and then calculate the events between each injection, each ignition event. Okay, so in the software, we're set up here. Never really has it become more important to label up your channels, because it really does get quite confusing when you've got 8 channels on the go. Your discipline has to be right on the money. You can see here with the channel labels that we've got crankshaft, all our cams. There's a section here in the middle as well to add all your notes. So bank to inlet, bank to exhaust. Your notes that maybe you want to add here, you can see I've got cylinder 1, IGT, L7, L being L for blue and 7 being pin 7. So you have an opportunity there to add more detail about the channel. Injector current for direct injector, and injector voltage for port. Now you'll notice here, because we're looking at port injector, remember we've got the attenuator on the front. It's 50 volts maximum input. Induced voltage quite easily will go above 100 volts, so we want to protect the front end there. Okay, so we'll run the engine. What I will do, I'll minimize the channel labels, because that just gives us a little bit more purchase here of the screen. And a nice feature here is the right click, and that's auto arrange axis. Yeah, or right click and reset view layout. So you can see the clarity that is instantly brought about by just right clicking auto arrange axis. Starting this vehicle, because it's a hybrid, we'll need to run a utility. So I just need to check at this point that the ignition is on, but we're not in ready mode. So yeah, we're fine there. We want this not to be in ready mode as though it were to be able to drive away. We want it in a mode where we can just run the engine as though we were going to do exhaust gas analysis. So follow the instructions on here. This will differ from vehicle to vehicle. It may be that you're not dealing with a hybrid. We've just got the added joy, if you like, of hybrid. So ignition on, ready is off. Click on next. Here we want to do a 4-wheel drive vehicle for measuring exhaust gas. And it's asking me now pretty much to put it in ready mode, which in layman's terms is start the engine. Okay, so our engine's running. We'll come outside of the ScanTool software. We'll run our scope. And there you are. We're triggering on channels A, B, C, D, E. Channel F we've got a trigger on. That's the ignition event for number 1. So everything commences from that point onwards. You can see here on channel H that we've got port injection. And at some point during the running, when the engine gets up to a certain temperature and the computer's happy with the running condition, it will switch from port to direct, and we'll actually hopefully capture that event. We'll hear the event for certain, and we'll capture it here on the screen. Clarity wise, your initial look at the screen there, you may think that there's way too much information and that it's not very clear because of the size of the axis. Remember, we use the auto arrange axis so we could get everything in line. All the features of PicoScope are there, so your zooming, your ability to right click and hide a channel, that's still there. So when it comes to the analysis side, we can make just one single injection event consume the entire screen and then correlate that maybe with an injection event. So you will not have, or you're not sacrificing anything in terms of screen space by having multiple channels. Where this really comes into its own is when we look at valve timing events, because dynamic valve timing, it's quite possible, and we have a scenario in an up and coming case study where you'll have mechanical valve timing check. So there's a manual rotation of the engine, aligning the marks. Everything appears on the surface to be there or thereabouts. When you actually do a dynamic test, so that's running the engine, looking at the relationship between the crank and all the camshaft sensors, you can see that there's a certain shift, because of course when the engine's running, we've got the additional load on the chain or the belt, any slack or any movement in a gear, that then will influence valve timing, and we can capture that certainly with the scope. So you'll see here I've got the properties page open. We could actually close the properties page. And there we are looking at all scope screen. Channel labels, you know, like I've mentioned here, they're all available. Yeah, don't really need them during your analysis, but certainly well worth it for when you're coming to do post-analysis checking, when you're looking at deviation, the fact that you've got it labelled up. Or even, let's say, for example, this file has to go off to technical support or to be shared amongst engineers. Label up every channel. Everybody can actually see not only what you were connected to, but maybe what cylinder you were referenced to as well. Okay, so we'll switch off at this point and we'll start to look at the software a little bit deeper and look at the relationships between cam and crank and just why dynamic valve timing checks are essential. So I talked earlier about this vehicle having port injection and direct injection. Now there's a facility within the scan tool to be able to force it to run either port or direct depending on engine temperature and other conditions that have to be met. So we'll just use PicoScope here along with the scan tool to change the direction, they call it injection way. So at the moment we're on either. You saw there, or you heard there, just that it flicked over to direct. And if you look at the pale blue, this is channel G, and channel H, the purple, you'll see, let me just go back one. You'll see in this area here that we were on port injection at this point here. You recognise this waveform. And then we switched from port over to direct. Yeah, we're looking at current. So yeah, just to clarify that this is port injection voltage and this is direct injection current, and that they are both for cylinder 1. And you can see of course that we don't have both there. One is switched off during the active test and then the other one commences. Using the signal generator on the back of the 4823, a typical example might be ABS wheel speed sensor with a square wave output like we have on this vehicle here. Identify the signal wire. Try and initially look for a good sensor. So go to, let's say, the left hand front if that's the known good, and rotate the wheel and capture the threshold. So that's the high voltage and the low voltage. It's a square waveform. We'll then replicate that using the signal generator. So we'll now go to the right hand wheel, locate the signal wire, and then we'll use the signal generator features to reproduce that signal. And then we can review the data on the scan tool data list to determine that yes, we've got a signal, that the ECU can interpret that signal, and therefore we've confirmed certainly the integrity of the signal wire from the ABS sensor back to the ECU. So let's run through that process now. On the scope we've got a double adapter, so this would be a single BNC to a double BNC. And why is that? That's so that we can use the output from the signal generator into channel A, and we can simultaneously measure the signal that we're putting out. Also, we're using our test lead to move down from the same adapter to the ABS sensor. So any voltage output from the signal generator will be measured by the scope and also forwarded or passed down to the ABS speed signal wire. So in the software, to go to the signal generator, we have this icon here. And the parameters we've chosen, we've gone for a 90 Hertz signal. We've gone for 1.95 volts amplitude, so that's from 0 to 1.95. And we know, because of a previous experiment we've done with this vehicle, we know that the ABS ECU can interpret that. So ignition is on. If I switch the signal generator on, we now see our square waveform there. And now let's flick to the scan tool view, and there it is. If you look at the right hand front wheel speed signal, it's 15 kilometers per hour. If I bring back PicoScope now, let's just pull this down slightly and let's change the frequency. So notice now how the graphing road speed is increasing. We're now at 51 kilometers per hour at 300 hertz. And if I bring this down slowly, 90 hertz, 80 hertz, there we are. And if we switch off, signal generator voltage goes to 0 and road speed drops to 0 as well. So there we confirm that the ECU can interpret the signal that we're sending to the signal wire of the ABS ECU, and therefore the integrity of the ABS speed sensor signal wire from the sensor under the wheel arch back to the ECU. Hello and welcome to the presentation for the new 4823 8-channel automotive PicoScope from Pico Technology. I wanted to start really looking at quad cam engines. This is a typical scenario where you'd require more than 4 channels. We've got a camshaft sensor on each camshaft, V configuration engine, and we want to look at the correlation between the crankshaft and the camshaft. So starting with the right click feature, auto arrange axis, and that immediately brings some clarity there because we've got all channels in use, and I will explain them. We've got a Hall effect crankshaft here, Hall effect camshaft sensors in ×4, ignition trigger signal from number 1 ignition coil, or to number 1 ignition coil from the PCM, so that will be your pulse width signal, so that would be dwell time across here, and then, or charge time, and then at this point here, secondary ignition event, that would be your fire point. This here is direct injection current, because this vehicle is fitted with 12 injectors, 6 direct and 6 port, and here are our port injectors. It's worth noting here we're looking at voltage on the port injectors, and of course the induced voltage is 116 volts. That will go above the rating of the front of the new 4823, so you're going to need attenuation for that. It's 50 volts maximum at the front end of the 8-channel scope. What we can say immediately is that this vehicle is running on port injection, because only port injection is active, meaning that the injection event is taking place on and around the induction stroke, whereas when we switch to direct injection, and we'll come to that a bit later, you'll see that we change the point of injection, of course, and we'll inject there on the on and towards end of compression stroke. All right, so let's bring a little bit more clarity to this. So let's just increase the scale for each one. We'll go to 0.5 for each. And what I will do as well, let's just zoom in on something like 720 degrees of rotation. So you'll see the missing teeth on the crankshaft pickup. That's better, yeah, that gives us, well, ignition number 1, back to ignition number 1 again, that's 720 degrees rotation. Alternatively, we could go from missing teeth on the crankshaft, again to denote 1 revolution. Let's bring these all up to the same size. It just makes things a lot easier when we're measuring. And the final one here, which I think is back to exhaust. Right, and let's just, I think we'll go for a little bit more purchase on the crankshaft because everything hinges on that signal. And then let's bring them all down into view so that they don't overlap. I'm not too interested really at the moment on what's happening with injection events at the bottom here, so these can pretty much just drop off the bottom of the screen for now. Right, so where are we going to measure from? Well, we use this to find our point on the crankshaft because we know IGT, or ignition event, whilst it does shift left and right slightly with advance and retard, that we could go for either or really, but I'll choose the ignition point here to identify this point on the crank rather than this one. Okay, so let's just zoom in on this area here. We'll grab this rotation ruler and zoom in to get absolute clarity on our 0 reference point. That's not necessarily 0 degrees rotation on the crank. That's what we're choosing as our reference point. We're choosing the missing teeth just before our IGT event. 1 revolution, 2 revolutions there. Again, zoom in to get as accurate as you possibly can. It's amazing how you can be just off the actual falling edge until you zoom in and measure. Okay, let's zoom in a little bit more, bring a bit more clarity here. Okay, so we'll now choose the first rising edge of each camshaft to measure. So the first rising edge after our missing tooth, well, we'll go first of all with the channel B, which is bank 1 inlet. And I've got these all labelled up at the bottom here so we can see. Try and be as accurate as we possibly can. So bank 1 inlet, 216, yeah, VVT disconnected, which is this one. Bank 1 inlet, 216.2, 216.3, we're not going to split hairs over that. The next rising edge is this one here. This gets us in the ballpark with a ruler. Try to be accurate as you possibly can again. And we are 184 for bank 1 exhaust. Bank 1 exhaust here, 184. So 184 degrees after what we've denoted as our 0 reference point on the crankshaft. And remember, we used IGT to identify which of the missing teeth we're going to use. Next we move to bank 2 inlet, which is the yellow one here. Zoom in. Okay, 93.7. Bank 2 inlet, 93.68. And then the final one, which is very close to our 0 reference point, this one here. Zoom in as much as possible. 5.64, we're 5.6. So we've got all those details there. And what have we proven? Well, at this stage we've proven that with the VVT system disconnected, that is the rest positions of those camshafts. And that would be the capture, or that would be what we would use as our reference, if you like, when we have another vehicle. We suspect a valve timing issue. We disconnect the variable valve timing control system, hope the cams revert to their rest position, they should do. And this would be a great foundation then for you to use as a reference. So let's bring in our VVT connected, which I think was this one, test 3, port to direct. I'll explain why we're going port to direct, or why we called the waveform that at this stage. Yes, this is the one. And we'll start again so you see exactly what we did with our capture. Reset the view layout. This feature, by the way, here, this is right clicking on screen to reveal this sub menu. So again, 8 channels, nothing's changed, the same orders are there, but we'll auto arrange axis, and then we'll increase each waveform's scale. So we've got plenty to measure, if you like. We're not going to make things difficult with the analysis. But what's important about this capture is, it doesn't say here, but VVT is connected. And we'll be able to prove that to you right now. Okay, and the red, that's bank 1 inlet. I need to increase that as well. And remember, we'll zoom in, we'll look for 720 degrees of rotation. Okay, and let's get some separation on these. Let's choose that same point. Remember, we used the missing tooth just prior to our IGT point here, not after. Okay, so bringing our rotation ruler from the right, Let's get right on the crankshaft, sorry, that falling edge. Again, apologies for keep saying that, but zoom in to get the best possible accuracy that you can for valve timing measurements. We don't really want to be anything other than a degree out if we can help it. We want to be able to have resolution or accuracy down to that level. Okay, so 1 rotation, 2 rotations, and we were measuring the first rising edge of each camshaft. Let's zoom in here to get a little bit more clarity. So the first one here is this point, and this is bank 1 inlet, 217.4. Well, I've measured this previously, but I must have been on a different point on the camshaft, because remember this is VVT, which will be changing depending on condition. Let's have a look. How accurate? Oh, there you are. There's a user error on my behalf straight away. Yeah, use the zoom feature, which I've just preached about. Now you get true accuracy, 216. So, clarify what's going on there. Bank 1 inlet has the same valve timing and cam correlation, I should say, whether the VVT is disconnected or connected at idle speed on a warm engine. So that's what we can conclude there. Moving now down to the green, which is bank 1 exhaust. Here, zoom in, and once more. Okay, now here we are at 202. So what has happened there? We were VVT disconnected, we were 184. Now with the VVT connected, bank 1 exhaust, which is this camshaft here, is at 202. So it's actually now retarded. Okay, so the exhaust camshaft on this engine, when the VVT is connected at idle speed and it's warm idle, is retarded from its rest position. Next camshaft, according to form, I should think it's the same, because it looks like the inlets don't change much. So we measure there 94, so bank 2 inlet with the VVT connected is 94. Okay, and then the final one is bank 2 exhaust. I think we can clearly see there's definitely movement, because that was very close to our reference point prior. 23.4, 23.6. Okay. So if you do the maths, I think this works out that the exhaust camshafts retard by approximately 18 degrees of crankshaft rotation, because with VVT disconnected they are 5.6 and the exhaust is 23.6 with VVT connected. So take one from the other, that would give you the difference. And the same again, we are 184 here to 202. So if we do the maths there on that, it comes out again around about 18, I think it is. So there's a revelation. That's what we've proved, or what we are proving, is that VVT operation is effective, and almost reverse engineering. We know that at idle speed, only the exhaust cams on this engine change, and they actually retard from their rest position. Inlets remained the same, didn't they? Bank 1 inlet, disconnected, and connected with 216. Again, 93.6 and 94.13, there or thereabouts. So we're good with that. Okay, so the final thing I wanted to show here was this switching from port injection, to direct injection. Let's bring these right way up and let's come all the way out and just concentrate on, let's go with this area here, and let's hide a few channels. So let's hide F, and purely concentrate on these events here. Let's get rid of the rulers. Sorry. There we are. So on this vehicle, we are looking at port injection, voltage, and I think this is cylinder 1. Let's zoom in again. It's a pattern we know and love. So pulse width, of course we can measure that for that particular one. Induced voltage as well. So pulse width we've got there 3.8. Induced voltage is peaking at around about 123, so remember, attenuation, very important. The pintle hump there, so we know that the needle is passing through the coil, the pintle, on its return when it seats down, so that's nice. So you've got all the resolution that you're used to with the 8 channels. We've got 8 channels active as well here. 2 million samples across the screen, 200,000 samples per second. So we're not losing anything. But you see what happens here right at the end of the buffer. Let me take away all channels so that we just focus purely on injection. So at this point here, injection or port injection stops, direct injection takes over. Now we are measuring the current, and I think it's through direct cylinder 1. So this is cylinder 1, direct injector, cylinder 1 port injector. And they're not running simultaneously, it's one or the other at this stage. Let's come back out, go to the next buffer. Buffer 6, we are now off port injection and running directly or only on direct injection. And there they are. So a really nice feature. And what I'm learning now using the 8-channel scope is just how much more there is to view and analyse, how much more can be revealed. No longer do you have the channel anxiety, for want of a better term. I know often we have to make a decision about which channel to sacrifice, what can I measure now, but now you've got 8 channels. You find certainly 6 you'll be using quite regular. I'm convinced of that. And then just having 7 and 8 is fantastic. So I hope that helps. And yeah, good luck. Enjoy. Hello and welcome to this brief video on the use of the signal generator, which is now included with the 4823 scope. It's something that we haven't seen in automotive with the automotive range of scopes, but certainly we can take advantage now. The options or signal generator menu is right at the end of all your channel options here. So after channel H we have the sig gen menu. Let's pull that over here. Okay, and first of all let's start with signal on or off and signal type. So the signal type that you want to generate, whether it be sine, square, triangle, ramp up, ramp down, sine X, so on and so forth. Let's stick with square wave because that kind of sits with things like duty and frequency control. At this point it's worth noting that I've got a lead coming straight off the signal generator and straight to channel A, so it's a short BNC to BNC, so any signals that we generate from the SIG generator will be displayed on channel A. So I've requested a square wave with a frequency of 70 Hertz, an amplitude of 2 volts and no offset. So let's have a look, see what that looks like. And there it is, we're generating that right now. If I slow the frequency down on this, let's take this down to 40 Hertz. You see that's getting updated there. Come down even lower, 30 Hertz, 20 Hertz. And then we can change the amplitude as well. So we'll put this down to 1 volt. So you see we are 0 offset, so 0 volt. No offset, sorry. And -1 + 1. Change that if we want to. We'll go for a sine wave. Notice how we update at the end of the buffer. Okay, because we're on 200 millisecond divisions, so as soon as we get to the end of the buffer, whatever we've requested in the signal generator will be displayed on the next buffer. Just change the triangle. There you go, symmetrical triangle. Let's go ramp down, so that'll be vertical, straight up with a ramp down. Okay, let's put that back to square wave. Next options, I do like this. This is quite unique. It's arbitrary, so this will be grow your own, create your own waveform. So we could go with this sine wave, something really obscure, and we click apply, OK, and then that same waveform will appear here, and we can amend the frequency and the voltage settings for that waveform. I wanted to show you a feature where you can add almost a glitch of your own. So if we click on here, and we'll draw something like that, click apply and OK, you'll see it there. I'm not sure where that might be useful. I think it's when you're trying to recreate events, maybe from a training point of view. That could be quite something to show a glitch. Let's go back to arbitrary again. We can import a waveform. So yeah, before we do that, let's cancel this. We'll stop for a second and we'll open a waveform so we can import a waveform. So if we go relative compression on this one, I think on channel A here we have a crankshaft sensor. Yeah, so let's hide a couple of channels. Keep A. Okay, we'll pull out a couple of rulers and we'll just zoom into this area here so that you can see what this is. You recognise that straight away. Inductive passive crankshaft sensor. Okay. Let's go back to our signal generator, go to arbitrary and go to import from a channel. So we'll import between the rulers, click OK, see it there, apply and OK. With this waveform now loaded into the arbitrary waveform generator, we can click signal on and we can run the PicoScope, and we have a trigger set on B, so we'll get rid of all the triggers. None. We'll get this into some kind of sensible range, so we'll go 5 volt and we'll reduce the time. Remember, this signal we are displaying is what we've imported from the waveform you just saw, which was a crankshaft sensor. There we go. If I stop that now. So the waveform that was originally on channel A, we imported. We use the arbitrary waveform generator, and we use the import feature. So the waveform generator recreates exactly what we captured originally on channel A. Okay, so I hope that's useful. So I'll look at sweep mode, and let's go back to a square wave. Let's run PicoScope to make sure everything is as it should be, and let's put it on a slow time frame, something like 200 millisecond division, so we can see in real time what's happening. Take the frequency down to 100 Hertz. Let's make a bit more use. Maximum voltage output from the signal generator is 2 volt. So there we have it, 2 volts, 100 Hertz. And now we have the option here to do something called a sweep. So let's stop the scope to avoid this distraction here. We'll ask the software to sweep up. We'll put a maximum frequency of 100 Hertz. We'll make the frequency increments every, we need to place a lower start frequency. So let's start at 20 Hertz. We will sweep up to 100 Hertz, and we'll do that in 1 Hertz increments, so every 1 cycle per second, and with a time interval between those increments of 10 milliseconds. Okay, the signal is on, and we'll run PicoScope, and hopefully you can see what's changing there. Drag this out of the way. So you see how we are sweeping up with a square waveform, starting at 20 Hertz with a 2-volt amplitude, no offset. Our stop frequency is 100 Hertz. The frequency increments every Hertz, 1 Hertz, and increment time interval 10 milliseconds. So if we were to put a math channel on that, we should see them, we could graph that and confirm exactly what's happening. So math channel, I've already got one here, frequency of A, okay. Notice the math channel is drawn at the end of the buffer. So we started low at around about 20 Hertz, you see there, and then we increased up to about 100 Hertz. Yes, there it is. Let's pull a ruler down so we can see that. Yeah, that's close enough. And we could do the other way. We can sweep down. Okay, so see how the math channel is graphing the opposite way now. We are starting at 100 and sweeping down to 20 at the same interval and the same frequency increments. What else have we got there? Up and down. Let's see what happens with the math channel here. Just ignore that for a second. There we go. So we sweep up and down. Okay. Then the final feature is trigger. So to avoid confusion, let's just remove the math channel. Math channel was frequency A, by the way. We'll take off sweep mode and we'll use a trigger on B. So whenever you've got your trigger source for your signal generator set to scope, it applies the scope trigger. So I'm going to put a repeat trigger on channel B, and let's have a look when our trigger level is. So we've got a current clamp on here, so that's not going to work. Let's put this just to a ×1 probe. Put it very low, so I'm just going to generate this with a spike of some sort, a bit of noise. And let's have a look at our levels. We make sure channel B is hidden. Was hidden. That's why we couldn't see the trigger or the channel for that matter. Okay, that menu there, that's a right click to reveal your channels. And we'll run the scope. So what's going to happen now? Hopefully I can introduce a spike on channel B. That will trigger a repeat trigger. Channel A is connected to the signal generator, and we should see a 20 Hertz 2-volt signal from the signal generator when the scope trigger has been compromised or offended or triggered. So let's try it. There we go. Stop the buffer, go back one. Let me just hide channel B. Okay, so we saw 20 Hertz signal, 2-volt amplitude, square waveform. So it's a single event. Okay, let's go to sweep mode. So sweep mode, we can actually apply the sweep features to the trigger. So let's bring back channel B. Sorry, let's run the scope. You can see that the CGen is running there prior to the trigger. Bring back channel B. Okay, so channel B is a repeat trigger. We're waiting for the trigger to be offended. I'll introduce the spike. There we go. And then the same rules apply there. So let's just go back through the buffer. We started to sweep up and down. So we started with a, well, we could measure that frequency, but you can certainly see that sweep mode was active rather than just having that single event that we did without sweep mode active, now the sweep features are applied to the SIG-Gen. So channel B, trigger, rising edge. That trigger was also applied to the signal generator, generating that fundamental signal with these sweep features attached. Final trigger settings or trigger source would then be manual, and in effect every time I press this button, trigger now, the trigger conditions or the signal generator conditions are met and will be displayed on screen. So to avoid confusion, let me take the scope trigger off, so the scope is just running now, or will be running, without a trigger. And let's turn off channel A, because A is not required here. And let's take sweep off for a second. Okay. So now when I press this button, trigger now, let's just go back through the buffer. Well, that's the signal that we constructed, and that would be a 2-volt amplitude, 20 Hz signal. So if we look here, that will be 40, because we want the same again, don't we, for the complete cycle. That will be approximately there is 20 Hz. Now I can change the cycle count here, so the next time this triggers, let's say we want 5 cycles per trigger. So let's do that again now. Take the rulers off. Trigger now 5 pulses. And let's keep triggering, keep triggering. There we are. Or we can introduce the sweep conditions. And notice at the moment we are on fixed frequency. Try and get this out of the way as best I can. Let's move these out of the way. Perhaps put the waveform up there. Okay, I'll press the trigger. Now, there we are. And again, you see how the sweep conditions are being met. So there you have it. That is a brief description of some of the options that you have within the signal generator. There's a lot more to discover. Remember, maximum output voltage is 2 volts. And yeah, be careful of the amount of current that you pull through there, because this is 5-volt USB, so current is absolute minimal. Alright, many thanks for watching. Take care.
Okay, welcome to our next Practical Pico segment, and in this section I'm going to show you how to do totally non-invasive testing of the immobiliser system, and this could be particularly useful if you suspect that you've got a non-start fault on your vehicle. Perhaps you've ruled out the fuel system and so on already, and you want to look at whether the immobiliser system is at fault. The way we're going to do this, we're going to look at the start of the process, which is looking at key data request from the key at the key slot. Then we're going to look at be checking the CAN signals to look at data there, so we can monitor whether there's any interruptions in those. And finally, we'll look at the end of the process, and this is all at the same time, of course, looking at a successful crank event, which will tell us that the process has worked. So without further ado, we'll begin the setup. So I've got the new 8-channel scope here, and to connect to the CAN bus signals, I'm going to use the breakout box here, and that will connect directly into the OBD port. So we'll just do that. So we're quite lucky on this vehicle. We've got both CAN high and CAN low speed signals available directly at the OBD port, and our box here shows us that we've got flashing here. So we've got pins 3 and 11 are the medium speed CAN, and 6 and 14 are the high speed CAN. So we'll connect up PicoScope to those channels. So we'll have the high-speed CAN high on channel A. Okay, so that's pin 6 on the box here. Then we're going to have the CAN CAN L, or the high-speed CAN low, if that makes sense, on channel B. Then we'll have, on the medium speed CAN, we're going to have the high line of the medium speed CAN on channel C, and that goes into pin 3. And then finally, we've on the medium speed CAN, but on the low line of the medium speed, which is pin 11 here on our connector, and then that'll be channel D on our scope. So I'll just go through that quickly again. We've got channel A is our high line of the high-speed CAN. Channel B is the low line of the high-speed CAN. Channel C is the high line of the medium-speed CAN. Channel D is the low line of the medium-speed CAN. Right, now all of those need a earth connection. Again, we can use our pins 4 and 5 on the breakout box for those. There we go. And we're all good to go. So that's our CAN networks all set up. Now what we want to do, as we mentioned at the start there, is if everything works, the engine should crank. So to do that, we'll connect just a really simple connection to the battery with one test lead. So we'll connect to the battery positive, which is here. And then if we find a good earth, got a lovely big bolt just here, straight under the chassis. That should do nicely. And then that can go, actually we'll put that in channel F, so that's our 6th channel. We'll go in channel F of the scope. Let's just make sure the leads are out the way of any rotating parts. Lovely, okay. Now here's the little secret weapon. This is actually our keyless entry detector. So we can look at remote central locking type devices with this, with the passive entry systems and so on. So we're going to put this into channel E, that's our 5th channel. So we've got A to D, our 4 CAN signals. E is the keyless entry detector, and then F is our crank event signal. Right, so we're all connected up. Now, the next thing is to look at our setup PicoScope and make sure that's okay. So if we go to PicoScope, now, going to give you guys a little bit of a treat. We're going to put this setup in the waveform library. So if you happen to have a 8-channel scope, then you can download it and just use the setup. If you've only got a 4-channel scope, you can still download it, but all you'll see is just the first 4 CAN signals set up. So if I describe the setup, now this is the beauty of PicoScope, and where we can really start to push the outer boundaries with our 8-channel scope here. So if we look at our window, and the first thing we can see at the bottom of the screen there are our channel labels. So that's labeling A to D on our CAN messages and CAN signals. And then on channel E, we've got our signal from our keyless entry sensor, which is the coil antenna energization. And then on channel F down here, you can see we're looking at battery voltage. So that will indicate the starter cranking. Now, if we minimize those for the minute, at the top of the screen, you can see we've got 4 views into these channels. On the top left, we've got what is looking at our key data exchange, our key data request. So that, as you can see, there's a trigger set on that. And so we're going to be looking at the signal from the keyless entry sensor, and that will tell us that the vehicle is looking for a key and wants to check that the data is okay. On the below that, we've got our cranking signal of battery voltage, and that tells us that will give us the exact time when the vehicle is finished, or sorry, started and finished cranking. And then over on the right hand side, so the 2 right hand panes, we've got a medium speed CAN and a high speed CAN. Now, on the medium speed and the high speed CAN, I've actually set up a maths channel, so we're not seeing the raw data to start with. We're just going to have a nice clean signal, which is on both cases is going to be the high line voltage minus the low line voltage. So that gives us our differential signal that is on the network. And that gives us a lovely stable signal from 0 to 2 volts on both the medium and high speed CAN networks. We've got a good reason for doing that, which I'll come to in a moment. And then finally, what we've also got on our top left pane is on our key data request signal. I've set a math channel to look at the frequency of that signal, which will show us the actual frequency of the signal, the energization signal that's going to the key. So we can be absolutely sure that what we're seeing is a real low frequency signal request. So that's those all set up. And then finally, on our 2 CAN networks, on our medium speed and high speed, we've got decoding on each of them. So we can look at all the individual messages on each of those channels. Now, the medium speed CAN in this case is set up to be on 125 kilobaud, so that's 125 kilobits per second on that particular CAN, and that's being triggered off the medium speed CAN maths channel. Similarly, on our CAN high network, that's 500 kilobaud, so 500 kilobits per second, and that one's being or is decoding, from our the high-speed CAN network maths channel. Okay, so we've got quite a lot there going on. We've got 4 views into our vehicle. We've got 2 serial decoding tables, and we've got all our channel labels. Plus we've got a trigger. So we are fully geared up to look at the whole process. So let's have a go at doing that. So we've got the vehicle here. Now, this is manual part of the operation. So I've already set PicoScope running. I should explain that. I'll just double set that. That's ready. So we've got the manual part of the operation here. So what we want to do is we take our keyless entry sensor detector and we put that as close to the key as we can whilst we do our start process. So on this vehicle, it's a case of I have to press the brake pedal and very quickly afterwards the start-stop button to get it to start. And the reason I want to press it quickly is because the actual key data exchange process starts when I press the brake pedal. So it won't look to see whether the key is a valid key until I press the brake pedal, which is indicating to the ECU, hang on, he's about to start the vehicle here because he's got his foot on the brake pedal. So let's have a go. So I'll put the key in the slot, brake pedal on, and crank. There we go. Okay, so I can see that we've captured that very nicely. I'll stop the engine. And I'll stop the scope. Let's go back to the buffer we've got the data on. There it is. Right, lovely. So we're looking here again now at our views. We've got on the top left, we've got a successful key request, so you can see a burst of activity there, which lasts about just over 0.3 of a second. Now, if you look on the math channel just above that, we can see that we've got the little variation in the frequency. So we've got frequency on the right-hand scale here, and that's telling us actually that's when the little data exchange is happening. So that's triggered beautifully, captured the whole thing. So off of that, we can then see that we've got our medium speed CAN has fired into action, and we've got a corresponding table of CAN events down there. Our high speed CAN has fired into action, and we've got another table there of CAN events going down. And then at around 0.85 seconds after the key data request, on our cranking signal, we see it at about 0.85 seconds, we've got the actual starter cranking. So just to reiterate one more time, here's the start of the process, here's data in between, and then here's the end of the process. So now the bit which can be the clever bit, there's two approaches you can do. We can either say one part of this process may have broken down. We may have not had a successful key data exchange. So we can see where we could have problems there, and we can see if that hasn't worked there. So the math channel indicates that nothing's been exchanged, there's nothing come back from the key. We could have intermittent problems with the CAN signals, which could be blocking signals via, say, the central electronics module, the engine control module, or the instrument cluster, that type of thing. So this scope setup is kind of network topology agnostic. It doesn't care what the layout of the control units are. It will just tell you whether there's going to be problems on the networks. So we can look at as I said, the quality of the data flow on the CAN messages, and then we've got the cranking to prove that it worked. Perhaps sometimes on intermittent faults, you might not get that crank signal. So this is the one good thing about intermittent signals, and this was a chap, Anthony Pickering, mentioned this. I saw this on social media last night. There is one nice thing about intermittent signals, is that the time that it's working actually gives you the good process. So you've got a reference there for the times when it isn't working. So we can have the same thing here. If we've got an intermittent fault, we can keep running the test. It's on a repeat trigger, so you can keep starting and stopping the vehicle to see when it's working, when it's not working. So finally, on the serial decoding here, if we're really keen, and I have done this before on another vehicle, on a Discovery, you can actually, we know, for example, that around 0.1 seconds is the key data exchange, and after about 0.8, 0.9 seconds, we've got the start of cranking. So in that time, that sort of 0.7 of a second, we know that the key data messages on the CAN network are going to be between those two time zones. So we can go through our serial decoding and look at the start and stop times and start to try, if we want to, we can export the data and start to do a further analysis of exactly which CAN IDs are related to the immobiliser exchange of data. So you'll get a kind of seed key type interactions between ECUs, and you can start to look at which ECU IDs send data, which receive data, and whether that goes across networks from medium speed to high speed via a gateway or something like that. So this allows you to unravel all that information, and we haven't taken one ECU apart, we haven't dismantled anything, it's all there ready to go. So I hope that shows you the power of what we can do with an 8-channel scope. You know, total system diagnostics is the big sort of USP of this beastie, and yeah, I hope we've demonstrated that in this segment. So we'll leave you to the next one. Thank you for joining me.
Hi there. Okay, so we're going to follow on from Steve and Barney's little bit about how they're using the 8-channel scope, and now for something a little bit different. So this is thanks to Charles Wilson at Huntingdon for allowing us to come into their yard today and actually jump on one of their machines. So thanks for that, I really appreciate it. So the whole purpose of this is to now look at a mobile hydraulic machinery and try and determine both sides of the system all in one go. And obviously using the new 8-channel scope, we have the ability to graph both engine related data and hydraulic system data as well. So with the scope and our setup, currently we have a engine speed sensor connected. We're looking at the voltages from 2 pressure sensors on the hydraulic main pumps. We're also using WPS 600 here as well to actually look at the physical hydraulic pressure in the 2 auxiliary pumps. We have WPS 500 on the crankcase, looking at crankcase pressure for obviously engine related issues, and we also have a current clamp wrapped around the starter motor to, one, give us something to trigger from, but also we can look at peak inrush current there as well. So without further ado, we'll get started and see what we've got. So we're running, trigger is all set up, we are good to go to give it a start. So one thing to obviously check when you're using pressure transducers is to make sure that they're switched on and fully charged up before using them. So we'll give it a go. Okay, so data is nicely captured on the screen. We took a really long amount of time just purely to try and get everything all in one go. Obviously with the cab round the front, all the leads are in the back with how I've set up the scope. So being able to capture all of that in one go is really important. But we can stop the scope now. And obviously using Pico's zoom features, we can actually highlight the different aspects of the capture. So you've got our engine speed here, which changes obviously as the engine starts. We have a standby pressure inside the auxiliary pumps as well here. One nice thing about the WPS 600 actually is we can now zoom in even tighter, and we can actually start to see the ripple that's generated from these pumps. So highlighting any further issues internally with them as well, just purely by connecting a pressure transducer. We can also look at the engine speed data, and obviously now with mass channels we can include them into the graph, actually look at the increase and decrease in crankshaft speed, again helping us highlight any potential issues with the engine, and also with the crankcase pressure. So here, as with some of our other recent Practical Pico sessions on non-intrusive engine testing, we can look at the pressure ripple from the crankcase and to identify other internal engine issues. So another use case for the 8-channel scope, we think it's a great bit of kit when you're trying to understand and get a better idea of how systems interact with each other, and for mobile hydraulics it makes perfect sense. Thanks for watching.
Okay, so thank you for joining us. We hope you enjoyed our presentations. If you have any further questions, then please feel free to write comments in the comment sections, and we will do our best to follow up with those. Equally, we've got our Pico forum on picoauto.com, and beyond that, we've also got our technical support line and picoauto.com itself. So feel free to get in touch with us through any of those channels. Thank you.
Thank you.